So I'm Valérie Guillerme, the same as during the presentation. So today I will start the workshop with a step aside CSP, as I will talk about SHIP, and I will give you an overview of the FriendSHIP project that is not focused on material and processes, but let's see what it is. And I will start first with some thoughts about the links between differences between CSP and SHIP. And well, if you look to the CSP panorama now, you are somehow entering the solar basis world. That's how I see that. And in this world, when you are talking about CSP, we are generally talking about solar thermal electricity. And for STE, the main competitors nowadays are other renewable for electricity like PV. And the main drivers of the development of STE is the cost, so the LCOE. And this implies that when you are working on CSP, generally speaking, you are working on very large project. Your projects are located in area in the world where you have very high annual DNI. You are supposed to work 24 hours a day, 7 days a week. So you are supposed also to have a large capacity of heat storage. And due to a search to better efficiency, you are going higher in temperature in the solar field and searching for higher efficiency in the cycles. And it explains a lot of works now in CSP in the field of new heat transfer fluid like liquid sodium particles or supercritical CO2 in the cycles. And it explains also that in the CSP landscape, we move from technology like PTC to towers due to the surge in higher temperatures. And one thing also is that in the case of CSP, you must connect to an existing electrical grid, generally speaking. One point here that I want to focus on is that this trend is also appropriate to the development of standalone technology like solar fuels or high temperature chemical processes for example, lime and cement. Now, if you look to SHIP or SIP, depending the location where you are talking about solar heat for industrial processes, the thing is a bit different as you are entering in this by the SHC world. It means a more world dedicated to heating and cooling and not to electricity. And so, well, again, SHIP stands for solar heat for industrial processes. And in this case, the competitors for SHIP are also other renewable for heat, like biomass. And the main driver in this case is not only cost, but at the moment more a ratio between cost and emission reductions. And this implies different things. One is that also your project is not standalone, means that you are certainly obliged to hybridize your chip equipment with an existing energy source. Also, you have to put your project in area with medium to low annual DNI. And what is also different between SHIP and CSP is that you generally don't need to supply 100% of the heat load and don't need, and this is not in this case mandatory to have a 24 hours a day, 7 days a week generation of heat for the process. You are working on smaller projects and interesting in the two main issue. One is the integration concept where you can plug your shipped equipment with an existing energy source, and integration also on site. So where can you put your solar receiver on site that are not desert? This is industrial site, so there is a lot of stuff here, and it is a major issue for chip project. And so to say that in the ship world, there is not only the very high temperature area, but there is two very interesting range of temperatures: the low range temperature and mid range temperature. Low range is up to 150 degrees, and then the mid range go up to 4 to 500 degrees. And you can see that there is there place for chance for concentrated solar technologies like PTC or linear Fresnel receiver, or compound parabolic concentrators for low temperatures. And well, this is a chance for those technologies that has been a bit updated by Tower in the CSP world. So this was my introduction, and now I will talk to you about the FriendSHIP project. So a bit of context: solar heat is already used for agro-food industrial processes, so mainly in the low range temperature, low temperature 50 degree. And the FriendSHIP project aimed to demonstrate that solar heat can also be reliable, user-friendly, high quality, and cost-effective the heat requirement for other industrial sectors as textile, plastic, wood, metals, and chemistry. So in this case, we are located in the mid-temp range. And so the four pillars of the project are to increase the temperature supplied, so to enter in the mid-temp range. Open application to cooling, we will provide cooling as in parallel with heat. Provide a better integrability into the process and support the solar stability of from the solar receivers. The project starts in May this year. This is a 48-month project, 5 million euros, and it has been funded by the European Union through the RES7 call dedicated to solar energy in industrial processes. We have 10 partners in the project, in the consortium: the CEA, SINTEF, National Institute of Chemistry, and INES. So those are 4 RTOs. And we have also 6 industrial partners. So Absolicon and Industrial Solar are techno providers for PTC and linear Fresnel. We have also RINA and Amires that are engineering and consultancy companies. And our end users are Sonai and Clariant, and Sonai from Portugal, which is a multinational company a wide portfolio of business. And Clariant is one of the world's leading companies in the chemical industry. If we look to the concept of the FriendSHIP concept, we want to propose system, two system, one able to produce together heat at temperature up to 300 degrees and negative cold down to minus 40 degrees. So there is two different system. One to address the 200 degrees, which is composed with a PTC, combined heat storage, an heat pump, and a chiller. And the other system, we replace the heat pump with linear Fresnel receivers to go to higher temperature. The SHIP 200 system will be validated on site in Grenoble, in CEA site. So you can see that the NI is medium, and I don't think you will try to put a CSP plant in Grenoble, but a ship plant, it's okay. And the second one is ship 300, and this system will be numerically validated using the data from our end users and their sites located in Deutschland, Portugal, and Spain. The expected improvement in the project are the followings. One is on the solar field, and we will work on local solar collectors with improvement on active coatings, and also a work on the improvement of heat transfer through addition of nanoparticles in the fluid. Another improvement will be to work on very high temperature heat pump. It will go high, as high to 180 degree first, and then on the long term, but it is a low-term work, up to 250 degrees. A very important work will be done on the storage, which will be combined. That means that the storage will be able to store the heat from the solar loop, but also to store some heat from the process loop itself. So it will be a component that will be the major equipment in relation with the process. So the integration point. A work on coolers, so cold production in parallel with heat, both using absorption or ejection chiller. And then, because we are working on a very complete system, and the system will be integrated in another one, we will work on an advanced control management that will ensure to rationalize the use of the existing energy source on site. And well, the impact, expected impact of the project will be that both systems will be able to decrease by 30% the CO2 and air pollutant emission of the industrial site where the system will be installed. So we start with work package 1 that will soon be off. So we advance on task 1.1 on the analysis of the requirements for the FriendSHIP system. We draft a list of technical and non-technical requirements, and so comes to key performance indicators that are the following: short payback period, high internal rate of return, high energy saving and CO2 reduction, high availability, high accuracy, temperature control, the flexibility to adjust to varying load, and compliance with relevant national and EU directives. So this is part of deliverable 1.1, which is not open and confidential. We also close our work on the definition of the technical specification for chip 200 and 300 system. And I'm running late in time, so I will not say too much about this. But perhaps just a few comments on one of the outcomes of this work is that we started to work on 2 systems, but at the end, systems are very related to the load profiles from the sites and their real needs. And so our 2 systems will be some option, and there will be the possibility also for the system to not to be full. Let's say, for example, in need of coal, there is no need of chiller. So the option will be evaluated to have those components as an option. Next steps. This is the next steps here. So we are month 6. We're almost finished with work package 1, and we're starting work package 2 to 5, which are dedicated to the development of the components. So solar fields, heat pumps, innovative cooling technology, and combined heat storage. And you can see that the demo will be started to be erected in 2022 for 1 year of test on site since 2024. So thank you for your attention. Stay tuned with the project. And if you are interested to help solar technologies to be a reliable part of process heat supply system, let's join the IEA SHT task 64, on solar processes. This is a joint task with solar bases. Thank you. And